Hello everyone, welcome to our PH 313. Today topic we are going to talk about is laser. So what is laser? Laser is an acronym. It's a shortened version of a long word, and that stands for light amplification by stimulated emission of radiation. So in laser, there are basically three most important atomic processes are happening, and they are: first, they absorb light, and then spontaneously emit light, and then they are also stimulated emission of light. We will see in detail about these atomic processes in next slides. Right. So what is this absorption? Absorption means if there is a incoming photon with correct energy, and this if it is coming towards a material, the atoms inside that material can absorb this energy. That means what really happens, in the atom, there are electrons orbiting around the nucleus of this atom, and these electrons can gain this energy and they can jump into a higher energy level from their ground state. So that we call the jumping from ground state to an excited state. And to do that, the incoming photon should have that correct energy. Correct, I'm emphasizing on this correct word, because if this electron, let me, please give me a minute to get the pointer. Okay, so this correct energy means if this is the ground state and if the electron wants to jump into the excited state, then this incoming photon should have the energy equal to the gap of this energy gap between the ground state and the excited state. And always this energy absorption follows the Beer's law, and the light will be absorbed according to the expression given in the Beer's law, and that is given by I equals I naught exponential negative sigma n naught L. These are standard terms. I'm not going to go detail into the Beer's law because you have followed Beer's law in various courses. So the absorbed intensity is related to the incident intensity through an exponential term. Right. So this is absorption. First, when incident photon or whatever, it can be a photon, it can be another type of energy incident onto the material, and then the electrons in the, now this material consists of atoms, and these electrons in the atoms can absorb, can gain this energy, move into an excited state. So this is basically the absorption. The spontaneous emission is one important atomic process in the lasing system. In spontaneous emission, what happens? The excited electrons, they are in a higher energy state. They are more, they are not stable, they are unstable. They want to come back to the state where they are stable. Like if we move to a higher position, we feel uncomfortable, unsecure. We always prefer to be in the ground state. Likewise, electrons also prefer to be in the ground state. So what they do, they drop back to the ground state, and by doing that, they emit their energy, the energy gap, or the energy that it absorbed as a photon. So the photon is coming out of the system. And these photons, they have random phase and random directions. Spontaneous emission we can't control. If the electron, if it is excited into a higher energy level, there, for a given excited level, there is a lifetime. Like the electron can be there for a particular time period. When that time expires, it has to come down by emitting a photon. So if it has a shorter lifetime, that means electron quickly jumps back to the ground state. So we can't control the spontaneous emission, and we can't even control their phase and their direction. So it has a random phase and random direction. And the rate of spontaneous emission is proportional to the number of atoms in the excited state. Right. So this spontaneous emission helps in lasing system, but into a small extent. But we need to further improve it to get a lasing system, or more atoms, more photons emitted with the same direction, same phase. So yeah, we'll see how we are going to achieve that. The stimulated emission is another concept. This was originally proposed by Albert Einstein in 1917. And he thus postulates that an electron is stimulated to go back to its ground state from its excited state by an incoming photon. Now in here, what really happens if now let's imagine the energy we are providing is an electromagnetic radiation. That means a photon is coming towards the material, and that material, the atoms inside the materials are already in the excited state. That means by previously they have absorbed energy, they are now in the excited state. And this incoming photon, it has this photon is electromagnetic radiation, and it has electromagnetic field. And that electromagnetic field can exert oscillating force on this excited electron in the higher energy level. And this the frequency of this oscillating force is the correct frequency. Then what happens? That oscillating force will influence this excited electron to jump back to its ground state, and by doing that it will emit another photon with the correct with that energy gap, so that we have the incoming photon coming out, and as well as this incoming photon's electromagnetic field exerted some oscillating force on the excited electron, and it forces it to go back to its ground state by emitting another photon. So we have two photons coming out of the system. So, so to do that, the incoming photon also has to have the correct energy and correct frequency. I mean, you know that the frequency can relate to the energy. By doing that, we have one incoming photon, and then we have two outgoing photons because of the stimulated emission. So this, if we can improve, then we can go for a lasing system. So here, this is a GIF showing what really happens. Okay. Now we have a ground state electron, incoming photon will excite it to the excited state, and then another incoming photon will force it back to the ground state, emitting two photons. So that is stimulated emission. So population inversion is another concept that we need in lasing the system. So if we can have more electrons in the excited state, then what happens? The more will drop and emit photons. That can be either spontaneous emission or it can be stimulated emission. So we need to arrive at a situation where stimulated emission is more likely than absorption, so that the laser beam increases in intensity. And we need to get more electrons into the upper excited level. And this is what we called population inversion. So basically, what we want, we need more electrons in the excited state, and we need to arrive at a situation where absorption, stimulated emission is more likely compared to the absorption, right? We will see how this population inversion is achieved in different laser systems. That is what we call pumping. Pumping means naturally lower energy levels are more heavily populated than high energy levels when we have thermal equilibrium. That means electrons tend to stay at lower energy levels rather in the higher energy levels, because they are unstable when they are excited. So we have, naturally, we have lower the excited state, lower energy levels, heavily populated. Then what we do, we continue pump energy into the system it can be incoming light, right? It can be an electrical charge. It can be a heating of the material, or it can be a chemical reaction happening inside the medium. So in this way, we try to pump energy into this system, and that pumping energy will be absorbed by the electrons in the medium or in the atoms of the medium, and then they will be excited into higher energy levels. So if we can maintain more electrons in higher energy state compared to the ground state, then we can achieve the population inversion to break the conditions of thermal equilibrium. Okay, now population inversion is not usually possible if we have only two energy levels, because when we start pumping, let's imagine we have a ground state, and at ground state we have 8 electrons and excited electrons at we have none. Then we pump energy, and part of these electrons will absorb this energy and go into a higher energy level. Now, what happens? Unfortunately, we can't exceed more than half electrons in the excited state. Why? Because in this situation, incoming flood of photons is likely to cause electron to drop. Now, we absorb some electrons are absorb some energy and jump into the excited state, and then we have, let's say we have all electrons excited, but continuously we have this pumping energy coming in, so that these pumping energy will cause the excited electrons to jump back down by stimulating them, right? By exerting and oscillating force. And some will drop down spontaneously. So this will come to an equilibrium, and we will have like 4 electrons in the ground level, 4 in the excited level, because at some point it's going to come to an equilibrium. So we don't have population inversion here. We just have same population in excited level and the ground state. So that's why we can't achieve a good lacing system using 2-level system. So we go for 3 and 4 level systems when we are constructing lasers. Okay, now we are moving to the 3 energy level laser system, right? So in this case, what happens? First, what we do, we have the ground level. I'm sorry if you can't see it. Sorry. The ground level is somewhere here, and then we pump energy. The incoming energy can be any sort of energy, and that energy will be absorbed by electrons in the ground state, and they will be excited first into the E3 state. So this is the pumping is the this process number 1. And then what happens? This E3 state has a very short lifetime. So electrons which are pumped up into this E3 level, they quickly drop back to E2 level because of the short lifespan of E3. And then what happens? E2 is a metastable state. Metastable state means it has a very longer, compared to E3, it has a longer period of lifetime. So when electrons quickly come to E2, it can remain there for a certain, it can be like milliseconds. So it can remain there for a few milliseconds, and then what happens? It will jump back to ground state, emitting photon. Now, how we are going to achieve population inversion here? Here, electrons in the ground state quickly excited to E3, then they quickly expire to E2. And by doing that, what happens? E2 will be crowded soon, because from E2 to E1, the dropping, it takes time, because they can live in E2 for longer time, and the drop rate is is relatively low. Therefore, we have more electrons accumulated in E2 and some will stimulatedly emitted, drop back to the E1, or some will spontaneously drop back to E1. So thereby the lacing happens between E2 and E1, and we have the E3 as the intermediate supporter to have the lacing action. So although stimulated emission still reduces our population inversion, the pumping is at a different wavelength. So you can see the energy gap between E1 and E3 is larger. Therefore, we need to have an energy. The wavelength should be, if energy is larger, that means wavelength is shorter. So if we are using some sort of a light source to excite these electrons from ground state to E3, we need to have a light source with different wavelength or shorter wavelength compared to this outgoing light. So let's say this, we use blue light here to excite the electrons to a higher energy level, but the lacing happens between E2 and E3 where energy is lower. Energy lower means wavelength is higher, so we have somewhere yellowish color coming out of the system. Even though the stimulated emission will reduce the population inversion, because in the lacing system we will see these outgoing photons, they are not directly coming out of the system at once. They will be bounced back and forth inside the lacing medium before they are coming out of the system. So when they reflect back and forth, what happens? These outgoing photons will again stimulate these electrons in the E2 to come down, emitting more photons. So stimulated emission is there, and stimulated emission still reduces the population inversion, but we have pumping at a different wavelength, and always pumping must exceed the stimulated emission. Otherwise, all the electrons are they are spontaneously dropping down, they are stimulatedly dropping down, and we need to maintain population inversion if we want light coming out of the system. To maintain that, we need to have higher rate of pumping. Like always, the pumping energy should quickly absorb by the electrons, and they go to the excited E3 level in a higher rate compared to electrons jumping from E2 to E1 via stimulated emission or spontaneous emission. Right. And then let me get my, sorry. Okay, now we have a 4-level laser system. Here also we have E1 here, that's the ground state. And then we supply energy so that this energy is a very high energy. That means a lower wavelength is used if it is a light source. And then what happens? The pumping energy is sufficient for the electrons in the ground state to jump into the E4 state. And if E4 is it has a short lifetime, so electrons in E4 will quickly drop down to E3 state. And E3 is again a metastable state, that it has a longer lifetime, and they will because the pumping, we do pumping at a very high rate, the E4 electrons in E4 quickly drop back to E3, and E3 has a longer lifetime, so it's the rate of coming electrons jumping from E3 to E2 is slow compared to electrons jumping from E4 to E3. So we have population inversion achieved at E3. Then slowly electrons from E3 to E2 will either spontaneously or stimulatedly emitted to the E2. That is where the lacing action is happening. And these emitted photons will be reflected back and forth in the lacing cavity. So these outgoing photons again will stimulate electrons in the E3 level to drop back to E2. But anyway, we keep the pumping rate high such that we always have the population inversion. So pumping rate is higher compared to the stimulated emission from E3 to E2. So the lacing action happens between E3 and E2, and then the E2, another quick transition to E2 has a shorter lifetime, and we want E2 to be that we have a population inversion. If N2 is small, it's easier for N3 to be larger than N2. Yeah. So we have in larger amount N3 accumulated, and we have, and for these electrons to drop down to E2, we need to have vacancies at E2. Therefore, we need E2 electrons to quickly go back to the ground level. And most probably this energy will be lost to the I mean, it will be absorbed by the cavity, what do you call the cavity walls, most probably. So it's always very important to, when we are constructing a laser system, this E2 and E1 is very critical, because these lost energies are absorbed by the cavity walls. And if the cavity diameter is smaller, more energy will be absorbed. So it's a very critical parameter when we are constructing a laser system. We need to take into account these electrons coming from E2 to E1, and we need, it's a design parameter that it goes with the cavity diameter and all. Right. So in 4-level system, the lacing action happens between E3 and E2. Okay. Laser construction. How we are going to construct the laser? Laser, there is an amplifying medium is the region where the population inversion exists. This means that the conditions are right in amplifying the medium for stimulated emission. So in the laser construction, first we will have some sort of a medium, and then we have highly reflecting mirrors. One is 100% reflecting or nearly perfectly reflecting, and the other is around 99% reflecting, and it is partially reflecting. Why? Because we have to allow some of this light to escape and come out as a laser beam. Even though if the lacing action is happening inside, if we don't let it come out of the system, we don't get any laser beam coming out. So that's why we have a mirror approximately 99% reflecting, and it allows only 1% to transmit out to the out from the laser the lacing this device. So here, this is the basic geometry of a laser cavity. In the laser cavity, we have these highly reflecting mirrors. One is 100% reflecting, one is partially reflecting. And then we have active medium. Active medium can be a liquid, can be a solid, can be a gas. And then we have some sort of a pumping source. Pumping source is a way of providing energy to the lacing medium so that we can excite the electrons in the medium to start the lacing action. And then we have the laser output, that is the partially reflecting mirror, some percentage of light that is created inside will be escaped out of the system. So that is lacing arm. So this is very simple schematic of optical resonator. So we have fabry-peratetalon. We, if you can remember, in thin film interference, we talked about the Fabry-Pera interferometer, and the most important part in the Fabry-Pera interferometer is the etalon. Etalon consists of two highly reflecting mirrors. Same here, we have two highly reflecting surfaces. That is, when we pump energy, this can be 3-level, this can be 4-level energy system. So electrons from ground state will be excited to higher energy level, and it will again accumulate in the metastable energy level. And then they, why we want these highly reflecting mirrors at two ends is now first electrons will jump down spontaneously. The electrons that are accumulated at the metastable level, when the time expires, when the lifetime is over, they will drop down to the lower energy level, and it will start spontaneously emit the light, the energy difference as a photon. And then these photons will go forward and will be reflected back and forth by these two mirrors. Then what happens, these reflected photons, the lasing photons will again stimulate the electrons in the metastable, accumulated in the metastable level, and then force them to come down to the lower energy levels, emitting the lasing photon. So that's why we need Fabry-Pera-Etalon in two ends of the optical resonator. So we have various types of optical resonators. We have plane parallel, we have two plane mirrors device such that they are parallel to each other. And then we have concentric or spherical type of mirrors attached to the optical resonator ends, or it can be confocal, hemispherical, concave, convex. So depending on the situation, depending on your medium, depending on your pumping source, these are applied accordingly. Okay, then we have the laser efficiency. Usually lasers are inefficient because the large energies are required to first to pump electrons from ground state to a very high energy level. So pumping energy is higher, therefore that is anyway required to maintain population immersion in 3-level and 4-level laser systems, because metastable energy level that helps keeping the population inversion active has a lower energy compared to the pumping energy source. So anyway, their efficiencies are generally far below 1%. Some reasons for this is pumping energy is considerably larger than the output photon energy. So the lasing system, the metastable energy, and either it can be a ground state, or in the 4-level system, it can be another intermediate state. The lasing energy, the lasing energy of the photons that are coming out of the laser system have a lower energy compared to the pumping energy that we use. Therefore, anyway, it's going to have a very low efficiency. High intensity pumping combined with high intensity of the laser beam means that the amplifying medium will get very hot, and it requires cooling. Very hot means you are losing energy thermally, and it will require some sort of a cooling mechanism. So this requires a lot of energy, even though the output energy is lower compared to the input and other cooling energy. And what are the laser gain medium? Now, I told you when we construct a laser system, we have Fabry-Pera-Etalon. Let's imagine they are plane parallel mirrors, and then we have the lasing medium in between in this optical cavity. And we fill this optical cavity using an active medium, and the lasers are classified into 3 main categories: gas, liquid, solid, and then we have the semiconductors. The first active media is a solid laser, and the active media was using a ruby crystal. So Theodore Meinmann was the first person to produce a laser, and this is a photograph of him using his laser. So you can see here, he has this helical shape of tube, and in the middle of this helical shape of tube we has his ruby crystal. So it's a solid one, a solid ruby crystal. It's like a cylinder. It is inside, and it is covered by a helical shape of a tube, and this tube is the pumping source. It has I think it has some sort of a gas. Let's see. This helical, this tube has a gas discharge. So the light coming from this gas discharge is directed towards this ruby rod, and ruby, the atoms in the ruby, the electrons in the atoms in the ruby crystal will get excited, and then the active medium is the ruby crystal there. Okay, we will see how this laser is constructed in next slide. Right, so the active medium is a small cylindrical synthetic pale pink ruby. Okay, here. So we have this ruby crystal. A ruby crystal is the active medium, and it is a small cylindrical synthetic a pale pink solid. This is synthetic, means this is naturally available, but for scientific purposes, we synthesize we artificially create them by introducing the amount of chromium. I mean that this ruby means it is basically aluminium oxide, and it has chromium inside. That this aluminium oxide is doped with chromium, and because of this chromium, it has around 0.05% by weight, and this ruby appears pinkish red because of the chromium atoms inside, and these chromium atoms, they absorb blue and green color, and if you take the color wheel, normally if it absorbs blue and green, if you check the color wheel, if you get the blue, and if you check the opposite color to blue, that is what it appears. I mean, this appears red because it absorbs blue and green, and if you take the color wheel, the opposite to blue and green is red. That's why it appears as pinkish red. And then what happens? They take this cylinder. The two ends are cut flat, and they are polished, and they are parallel to each other and normal to the axis. They are parallel to each other and normal to the axis. And then what happens? They silvering. This is 99.99% reflecting, that is totally reflecting, and this is around 99% or 98%. This is partially reflecting, so that it can, some light generated inside can escape from this, and we receive them as laser light. So that is the laser output. And as I told you, this ruby crystal is covered by a helical flash tube, that is for optical pumping. So we optically pump it. What really happens here? We have two electrodes, and it is surrounded by this helical gaseous discharge flash tube. These electrodes provide energy to the gas, and that gas will start glowing when it is excited, and that glow, that light is absorbed by the ruby crystal. So the ruby absorbs, because ruby appears red, ruby absorbs blue and green. So this gaseous discharge should have green and blue light coming out of it, and that green and blue light is absorbed by the ruby crystal and starts exciting their electrons in the ground state to an excited state. Then what happens? They quickly expire to the metastable state, and then from metastable state they are accumulated, population inversion is achieved, and then electrons in the excited state, the metastable state, slowly coming down to the ground level, and because this is a 3-level system. And then what happens? The spontaneously emitted light is reflected back and forth because of this silvered sides. They are reflected back and forth, and then when they are reflecting back and forth on their way, what happens? They stimulate, they exert oscillating force on the electrons accumulated on the this lacing level or this metastable level, and force them to drop down, because the pumping rate is, the electrons absorbing energy at a higher rate to excite into the higher energy level compared to the stimulated emission. We get a good laser light coming out, and this laser output is around 694.3 nanometers. So this is reddish in color. And if you check the beam here, this is the beam. This is the beam. You can see it is kind of the full width at half maximum is what we use to define how sharp or how good the output is. So you can see if it is a broader one, that means it has other wavelengths included as well. But if you can achieve a very sharp output line, that means the wavelength of this output light is we can clearly say it's monochromatic. So we can achieve a good monochromatic light coming out of the system. Okay, this is okay, I think you can't see the bottom line. There's the ground state at the bottom that you might not be able to see it. So you can see this is the laser transition. So this blue and green region are absorbed by the ruby crystal, and then they jump into higher excited levels. So this is pumping, this is again pumping. So we just have to make sure that helical gas discharge has blue and green light coming out of it, so that electrons in the excited state in the atoms of the ruby crystal will be excited to higher energy levels, and then they quickly expire to the metastable state, where they accumulate to achieve the what do we call the population inversion, and then they start dropping down spontaneously, and these spontaneously emitted photons will be reflected back and forth due to these highly reflective mirrors on sides, and then these they are on their way, back and forth. When they are moving, they will exert oscillating force on these accumulated electrons in the metastable state, forcing them to drop down to ground state without completing the lifetime in the metastable state. So there we have stimulated emission coming out, and because of the partially silvered mirror in one cavity, this lacing light will be escaped. Right, I think I explained this. So pumping rate we have to increase, otherwise we can't maintain a population inversion. The first few spontaneously emitted photons will stimulate the chain reaction via doing this stimulated emission. And emitted photons are in phase, and it has the same polarization, and it propagates in the same direction as the stimulated photon. So the radiation, this we say it has same radiation mode as the incident wave. Since one mirror is partially silvered, intense pulse of red laser light of wavelength 694.3 nanometer will emerge from that end. Here, the broad absorption bands of ruby crystal makes the initial absorption easy. Now, not only a single wavelength is absorbed, it absorbed two energy bands. One is in green energies, one is in blue energy. So we have multiple. We can excite the electrons in multiple ways by providing blue light and by providing green light. So it makes the excitation or initial absorption process easier, and then it has a longer lifetime of the metastable state, and that facilitates the population inversion. The atomic system, in fact, consists of absorption bands and metastable state and the ground state. So the first laser system is a 3-level laser. So then, depending on the active medium of the laser, they can be liquid, they can be solids, they can be semiconductors, or they can be gas. So in the gas, what happens? In the gas, they have gas atoms. So we have atomic process here. So the gas, what happens? The electrons in the lower level in the gas atoms will be excited to higher level, and then here this metastable, the one I described, it will be excited to higher energy level, that it has a shorter lifetime, and then drop down to a metastable level to achieve the population inversion, and quickly drop back to the and then drop back to the ground state, come with lasing action. But this can be, I mean, this is not a fixed way. In a 3-level system, there can be, depending on the atom's electronic configuration, we can have where the atoms are directly excited to the metastable state. So we achieve the electron population inversion directly by pumping them to the excited level. And then because this upper level is metastable, they will drop down to another level and then quickly decay. So we can manipulate the system depending on the conditions that the atoms offer in the gas medium. But normally we have upper laser level where it has a shorter lifetime, and then they drop back to an intermediate level, and then rapid decay down to lower level. So lasing action here, because the population inversion is occurred at, if the metastable is the upper excited level, then we have the population inversion occurred at upper level, and lasing action, because stimulatedly, either spontaneously and stimulatedly, these lasers will be dropped down to another intermediate level and then rapidly decay, and they will most probably losing their energy to the boundary of the optical cavity. Or it can be the way that I initially described. So this is 3-way. And in liquids, or most probably they are dye lasers, first they are excited, and then they will be drop down to the metastable level, and then lasing action, they will drop down to lower ground levels. Solid state, like in the ruby crystal, for example, they will also first excited to an upper excited level, and then because it is unstable, that means it has a very short lifetime, they will drop down to a metastable level, and then through spontaneous emission and then through stimulated emission, they will drop back to an intermediate level, or they can and rapidly decay by losing the energy to the boundary of the optical cavity, or directly they will drop back to the ground state, depending whether it's a 4-level or 3-level system. Semiconductor it's kind of a different. In semiconductors, they will have P and N junction, PN junction, and I will describe how this is happened, because electrons are injected, holes are created, and then their population inversion is achieved in semiconductor lasers, and then lasing will occur. Okay, population inversion in gases. So we have a gas as the active medium inside the optical cavity, and this produced by applying a voltage across the gas discharge tube with electrodes installed at each end of the tube. So here, these are the ends, and we have electrodes attached. And then we input very high supply of voltage apply across, thereby ionizing we create a plasma inside. The gas tube is filled with a low pressure gas, so it can be a pure gas, it can be a gas mixture. Then applied voltage produces electric field within the laser tube, and that accelerates electrons within the gas. So that means you basically create a plasma inside. Those electrons collide with gas atoms, excite the atoms to an excited energy level. So we have high when we apply high electric field, what happens? There can be an electric field within the laser tube, and due to this electric field, the electrons are accelerated inside the gas, and these accelerated, highly fast moving electrons will collide with the gas atoms, and they will be excited to higher energy levels. And these excited atoms will come down to lower energy or lower energy level by emitting electrons. So the gas system, I think most probably they have the upper excited level as the metastable, where you achieve the population inversion. But that can be different for different gas atoms. We will look into few gas laser systems. Normally we have atomic lasers like helium neon, which produces around 632.8 nanometers. And then we have ion lasers where normally it's argon ion laser that produces green and blue-green. And then we have molecular laser. If it is not atomic gas, then it can be a molecular gas like carbon dioxide or nitrogen likewise. The carbon dioxide is very popular producing IR laser, and nitrogen produces UV. And then we have the same thing under the molecular laser. The excimer laser is also coming out. That is actually it has sort of a chemical reaction is happening inside. In the excimer laser, like argon fluoride, krypton fluoride, xenon fluoride, they produce electrons, they produce light somewhere in the UV range. Usually in these type of lasers, like excimer lasers, it has a mixture of halide such as fluorine and a rare gas like argon. It's filled. It's a mixture, a gas mixture. It is filled inside the discharge tube, and then electrons in the discharge tube dissociate and ionize halide molecules and create negative halide ions and positive rare ions. And then what happens? Argon is positive, fluoride is negative, or the halide is negative. Gas, the rare gas, they are, when they are ionized, they are positive. They get together, produce argon fluoride excited level. There should be an asterisk here showing that it's an excimer. Argon fluoride molecules in the first excited bound state, followed by their transitions to the repulsive ground state to commence lasing action. Okay, you can read more about these excimer lasers if you want to, but I'm not going to go into detail because there's a lot of chemistry involved. Right, this helium neon laser is very unique. Like in the helium neon, the first helium neon, they start producing lasers in IR region, and it again it was around 3.39 micrometer, and then we had 1.15 micrometer. Both are corresponding to IR region, and then we have 632.8 nanometer. So this helium neon laser is able to produce 3 laser wavelengths. So by having some filters, we can filter out the unwanted lasing actions. If we want like visible red light, we use most commonly that is 632.8. We filter out we have some filters to filter out the IR region lasing. So only red light is coming out. So this is a 4-level laser, and why we have helium neon, not like the argon and let's say the halide and the rare gas system, where there's like a reaction is occurring. Here, neon, the helium basically helps neon to lasing action. What really happens here? Let me see here. It's right. So in 1961, if I talk briefly about the helium neon laser history, in 1961, Ali Jawan and his associates reported this continuous wave helium neon gas laser at around IR region 1.15 micrometer. But if you can remember, the solid laser I talked about, it is a pulsed laser. So you pump some energy, there's an output. Then again, you pump some energy, there's an output. So we have a pulse laser coming out, not a continuous one. But in the helium neon laser, this is the first laser system that could produce a continuous, I mean, when it starts producing, it's not pulsed, it's continuously. In solid state or in these pulse lasers, if they want to like achieve some a laser that is close to continuous wave laser, what they do, they pump in a very rapid way. Like pumping rate is very very high, so it's like picoseconds like this. It's very quick, but still it's pump. The light comes out as a pulse. But this is a continuous wave laser. Now, modern day, we frequently use this helium neon laser in 632.8 nanometer. Right. So the pumping is achieved by electrical discharge, and that will first generate free electrons and ions. So this electrical discharge will generate free electrons and ions. They are accelerated by applied field. Then what happens? These accelerated electrons and ions will collide further to ionize and excite the gas medium. First, what they do, they interact with helium, and helium electrons will be excited to upper energy levels. First, what happens? They will be excited to higher energy levels, and then they will drop back to these metastable levels. Metastable levels. The first metastable that it has. Various atoms will have various number of metastable units, but here in the helium it has basically two metastable states. One is the 2,1s and the other is the 2,3s. Then what happens? The excited electrons drop back to these metastable levels, and they start accumulating at these levels. Then what happens? These electrons, even though they are now accumulated in these 2,1s and 2,3s states, this is a singlet, this is a triplet state. What happens? They are still excited helium atoms. These excited helium atoms, then what happens? They are inelastic. Now gas atoms are moving. These excited helium atoms collide with neon atoms. That happens, and that collision is most of the time it's inelastic. Inelastic means helium will transfer some of its energy to these neon atoms, and these neon atoms, what happens? They will be anyway. Some of these neon will be excited because there are electrons colliding. Right? There are fast moving electrons because of this electrical discharge. these electrons and ions will excite not only helium but also neon. But these helium atoms, when they are excited and collided with neon atoms inelastically, some of their energy will be transferred to neon. And that is possible because these excited electrons are in these excited levels and they are comparable with some energy levels in the neon, because they can quickly inject energy. Like this electron, this extra energy that this helium atom, if this helium atom's electron is, let's say, it's accumulated in this triplet state, that energy is comparable with two-way state of the neon. So it can quickly transfer that energy, give it out to the neon, and neon quickly transfer its electrons to this two-way state. Right? Same here, if this helium atom, the colliding helium atom, let's imagine the helium is now colliding with neon, and this helium is now an excited atom, and that excited electron, let's say it is now in the singlet state. In the singlet state, it is comparable with the 3s state of the neon, so that it quickly can transfer its energy. That means this neon atom is capable of absorbing that energy because that is correct energy for it, so that it can transfer the electrons in the ground state to this 3s state by absorbing that energy. So that this helium and neon, the helium can, when it is excited, has the correct energy so that it can excite the neon. So that in elastic collision, make these neon atoms to excite into higher energy level. And if electron is excited to 3s level, they will drop down to 3p, emitting 3.39 micrometers. Because this is a metastable level, population inversion is achieved. Then what happens? The lasing action is happening here. This 3s can drop down to 2p, but 3s is not allowed to drop down to 2s. You have to remember that. But 3s is allowed to drop to 2p, and when they drop to 2p, they emit this famous 632.8 nanometer. Let's say the collided helium, excited helium atom had electrons into 3s state, that is in the triplet state. Then, because this is also correct energy for neon, this neon in the electrons in the ground state will quickly absorb this energy from helium and excite its electrons to 2s state. The 2s electrons are allowed to go down to 2p by emitting 1.15 micrometers. So these are the three lasing wavelengths that are coming out of the helium neon laser. If you require a mid-IR, then you can filter out the rest and allow only 3.39 to come out. If you are after, let's say, near IR, then you can filter out 632.8 and 3.39 and allow only 1.15 micrometer laser to come out. If you are after visible wavelength, you can allow 632.8 nanometer light coming out, and you can filter out the IR region. So this is a 4-level laser system, and if anyone asks you what does helium neon laser does and what is the, are they both, like, if they know about laser and if they're just curious, out of curiosity, they ask that is helium and neon both are in the lasing action? No. Helium is just an intermediate agent that supplies energy to neon so that neon can do the lasing action. So helium is an intermediate action. Same way, I think nitrogen in molecular laser, like let's say carbon dioxide, I think nitrogen serves as an intermediate. So they have a gas mixture, they have nitrogen, they have carbon dioxide. Nitrogen first gets excited and then inelastically collide with carbon dioxide molecules, supply energy to these carbon dioxide molecules, and then carbon dioxide will do the lasing. Okay. Oh, the spontaneously emitted photons, as I told you, even in the neon, when they start lasing, The first spontaneously emitted photons initiate the stimulated emission because they are not allowed to escape directly. They are reflected back and forth inside the optical cavity, and then they start stimulated emission, and chain reaction therefore begins. So we have three dominant laser transitions corresponding to IR region and visible region. The P states drain off to S states, continuously sustaining population inversion. 1S state is metastable. Okay, let's go back to the yeah, okay. So we have the P states drain off to 1S states. This P will go to 1S state because here continuously sustaining the population inversion. So to maintain population inversion, right, we need to have more vacancies in 3P or 2P because we need to have vacancies so that these accumulated electrons can easily come down. So 3P and 2P, these P states, they have very low lifetime because they need to drain their states in order to receive more electrons come stimulatedly dropping down to them. So that's how they continuously sustain this population inversion. And 1S state here, 1S state is, it says metastable. 1S atoms return to ground level, like as I told you in the 4-level system. From this metastable population inversion is here, they drop back to intermediate level and then they fastly decay into this level. And from 1S state to neon, they will lose their energy due to wall collision. So these energies will be lost to the optical cavity boundaries. So that's and 1S atoms return to ground level after losing energy to the walls of the enclosure, the optical cavity. This is why the plasma tube diameter is inversely affects the gain and is significant design parameter. So you can see if the diameter is smaller, then what happens? More energy is lost to the wall, therefore gain is larger, right? So they quickly drain it and more lacing action is happening. So that's why plasma tube diameter inversely affects the gain. Okay, right. Argon ion, I'm not going to talk about these states because these are deep chemistry that I don't have time explaining them. So you can see there are like several, now these are the spin state, like I told you in previous one also, triplet state and singlet state. Some of you may know, some of you may not. Triplet, singlet, they depends on the spin. If they have a spin half, then you can go for negative half, 0, positive half. So that way, that's a triplet state. Singlet state, you have 0, like in the Pauli exclusion principle. The spin, the spin cancels out with each other. So you have 0, so you have only one level. Likewise, so I'm not going to go into details. So you have argon laser is, you have the ground, argon atom in the ground state. This is argon ion in the ground state. An argon ion and fluoride ion creates this excimer at level 1, and that's where your lacing is happening. So they can provide green, blue, and blue-green. This is carbon dioxide that can produce lacing in IR region. Similar to the helium in the helium neon laser, nitrogen here serves as an intermediate in carbon dioxide laser. So first it is filled with a mixture of carbon dioxide and nitrogen. First, nitrogen absorbs the pumping energy, gets excited to higher energy levels, and they have these metastable energy levels. Metastable energy levels here, so that when they drop down to these metastable level, then these excited nitrogen atoms collide with carbon dioxide, because their energy, this metastable energy and this metastable energy is like they are energy wise comparable. Inelastically it will uh, give out some of its energy to carbon dioxide, and then what happens, the ground state electrons will get excited to these metastable levels, and then lacing will happen, and then they will quickly decay to lower energy levels so that they can sustain the inversion, population inversion at this point. And then what happens, these electrons at this intermediate level will drop down to the ground state via uh, collision. They will lose some of their energy via collision to the walls of the optical cavity, or it can be radiative decay. Okay, and here I forgot to tell you energy level diagrams for molecular laser systems. You need to consider, because this is a molecule, not a single system, it has 3 atoms there. So atom starts vibrating. This vibration can be 3 types. One is symmetric. This is here. This is symmetric, and this is bending, and this is asymmetric stretching. So this vibration is in 3 ways, and that requires 3 types of energy, quantity wise. Yeah, I'm not going to go into more chemistry side. I'm just basically telling you this. Right, because my battery level is low, I'm going to stop it here. I will be talking about population inversion in liquids and semiconductors in next video. Okay, thank you.